elastic load balancer in our account so that you can distribute traffic between multiple instances. First we will see why we need a load balancer. Then we will see what are the different components Amazon offers to set up a load balancer in your account, and what are the different types of load balancers itself are there, and how to set up health checks, how to set up listeners, which ports and protocols. All those things we will see today. So again, ELB is part of the networking group of services offered by Amazon, and we have already seen how to set up our VPC. Now we will go ahead and see how to set up our ELB inside our VPC. So I'm going to refer to load balancers as ELB, that is Elastic Load Balancer, and quite often people refer it in the same way in the industry also. So without a load balancer, this is what happens on the background for your web servers. So say there is a single request that is coming in, and then there is only one instance up and running in your environment. It's very easy, all the requests go to one instance. But what happens when more traffic increases and you would want to scale up your instances, then you will probably add a couple of more instances in your account. But how do you ensure that the instances are receiving the traffic in a uniform way and all the instances are utilized in an equal way, so that there is no latency problems with particularly some users? As you can see here 2 users are hitting one server, another 3 users are hitting another server, whereas a third server is sitting idle. There is no easier way to solve this problem unless you put something like a load balancer in front of these instances, which will ensure that all the traffic is distributed equally among all the 3 servers. So this is why you need a load balancer in your environment. And there are other functionalities also that the load balancer provides. For example, offloading your SSL traffic, or defending against a DDoS attack, or you can also configure it for high availability also of your machines, because you're doing health checks, and if your server goes offline, the load balancer will intelligently stop sending traffic to the failed machine, and it will send the traffic to the remaining machines. So your user experience is improved by all these mechanisms. So when you are talking about elastic load balancer, that is AWS ELB in particular, it is quite elastic, like many of the other services. You configure your ELB, and then whether you have 100 requests or 1000 requests or 1 million requests, the ELB will scale up or down as you need it. And you can put your ELB inside your VPC, and you can set up a separate security group, separate subnets, and you can configure SSL, TLS. So all these ways enable your ELB to be really secure when it is receiving the traffic and sending the traffic back to the internet. And you can think of ELB as your frontline defense when you're facing the internet. And you can configure ELB to send your traffic to an EC2 instance, or you can configure it to send it to a container-based services, or you can also configure it to send it to your on-premise private IP addresses also. So it is very well integrated with a lot of other services, and it can play nice with your on-premise systems as well. And given all these benefits, yes, it is cost effective, I would say. Quite often, whenever we want to put something internet facing, the most common recommendation is put an ELB in front of it and use only the ELB IP address, because it has been designed for facing the internet and it is built for security in the cloud. So the ELB architecture, or where an ELB comes in, looks something like this. As a reference, you have a VPC, and there are a couple of subnets inside that VPC, and each of those subnets have some web servers or app servers which need to be internet facing. Then what you do is, typically you can set up your own separate VPC for your ELB and create 2 subnets for your ELB and create an ELB inside them, and you connect to the application instances on the background. So how are you on the front of your ELB? Again, you will have a Route 53 or some kind of a DNS service that will be sending your traffic. That will typically be sending your traffic from here. And again, your ELB can also send 1:1 mapping, or it can do something like this also. This is also possible today with the ELBs. So let's go ahead and see some of the other features offered by ELBs. As I spoke earlier, you can configure it for an instances inside your VPC, and it supports both public and private IP addresses, and even enterprise IP addresses, which is in your on-prem servers, assuming you have a VPN setup and networking is all set up. And then you can have full control over the security group, whether what kind of ports the ELB should receive, what kind of ports it can return back to, and what kind of protocols, whether it is HTTP, HTTPS you want to support, or whether it is TCP only that you want to support. So you can have control over the protocol as well. And we have very tight integration. You don't have to do literally anything to set it up with other services, which it plays nicely with, whether it is a certificate manager, EC2s, VPC subnets, or monitoring in terms of CloudWatch, and all those things. It is integrated, and all, whether you have to choose whether you want it or not. So let us ignore this one. It's supposed to be not there. And this is the two types of load balancers that are offered by Amazon, classic and application. When you're talking about a classic load balancer, until a few months ago, there was only one type of load balancer available in Amazon, that is working at a network layer. If any of you are familiar with OSI, 7 layers of OSI, the classic load balancer used to work at the network layer. If I'm not wrong, it was at level 4. And it used to support the TCP, SSL, HTTP, HTTPS protocols, and it was working with both classic VPC and the latest version of VPCs, and it supported CloudWatch and health checks. But Amazon found that people want an application level load balancer to support the latest applications like Node.js or AngularJS, where you want to have multiple routings possible at a software level. Then they created this application load balancer and renamed the older one as classic. Whereas when you come to application load balancer, at OSI level, it performs at the layer 7. So it supports only HTTP and HTTPS, and it works in the current version of VPC only. So if there are people who are running AWS for almost 8-9 years, for them there is something called as a classic VPC. The functionality of classic VPC is slightly different, but that is no longer supported or not even publicly available anymore to start your resources there. So application load balancer cannot be set up there, and it supports WebSockets, all the latest support that you can expect from a modern load balancer. You can get it in an application load balancer. So when we are talking about it, it's a summary of the things that we just now spoke about. It is at layer 7, it is fully managed, and it scales automatically. All the scalability, integration, security of the classic load balancer appears here as well. The content-based routing is something that we will see later. I'll show you typically how the content-based routing happens. So when you configure an application load balancer, behind this one you can have multiple applications. Say you can have your corporate HR application, you can have your payment or tax related information, or you can have your leave management system. All of them can have the same source URL or domain name saying www.mycompany.com. When you say /HR, then it will take you to a different group of applications. If you say / tax payments, then it will take you to a different set of applications. So depending upon the type of URL, application load balancer can send your traffic to different applications. So typically a classic load balancer will look something like this, and user is there and ELB is there. It cannot differentiate the traffic by looking at the traffic itself. It just forwards the traffic to all the listeners it has on the background. Whereas when you put it in an application load balancer, it can see what is the traffic, what is the URL coming from. It is orders.example.com in this case, and images, it will send it to a different group of applications. So this way one load balancer can connect to multiple different applications on the background, and you are becoming cost effective here instead of setting up multiple load balancers. And this is another example where you are looking at the subdomain, the prefixes, suffixes of the URL itself, say /orders/images. So this is also possible in your application load balancers. Earlier it was different URLs configured for the same ELB, here the same URL but different suffixes. So this is, I saying, cost effective. You can, instead of running multiple load balancers, one should be more than enough for you. So I spoke about health checks being done from your load balancer. The idea is, if you have 3 or 4 instances, how does your load balancer know that all of them are functioning properly and which one has failed or which one has impaired? So it is possible to configure some health checks so that your load balancer will constantly ping them in a particular port number, or try to request for an page and see whether it is receiving an HTTP 200 error code, response code, or it is getting an error code. Based on that, it can define whether that instance is failed or it can continue sending the traffic. Of course, you can also configure ELB updates through CloudWatch also, but a simple health check doesn't need to connectivity to CloudWatch. You can just do it through port or protocols or URL based health checks. Here is a simple example. There are 3 instances and all of them are functioning properly, all of them are healthy, but after some period of time you find that the instance number 1 has more CPU consumption. The utilization has gone high for some reason. It might be hardware failure or it might be having some memory leakage on the application level. So if latency of that instance is increasing, the ELB will understand that there is some problem with that instance and it will stop sending to that stop sending traffic to that instance. And since it stops sending, the utilization of the other 2 servers will also increase marginally, because it is sharing the load of 3 servers now and there are only 2 servers available. So after some time, let us say somebody has noticed this and fixed the problem with the other server. They have brought the 3rd server also into a healthy state, and if they don't have to do anything, ELB will start pinging the server because the health check is configured, and if it understands that that server has come back online, it will start sending traffic back to the server, and the load on the other 2 servers will also gradually go down. So that is how ELB does an health check, understands a failed instance and stops sending traffic, but it receives a notification saying everything is fine. It will accept that new server and start sending traffic again. So the health checks can be configured in multiple ways. As I was saying, support for TCP/IP pinging is there, or if you want to do it URL based health checks, you can do it with HTTP or HTTPS, and you can set your frequency as you need it, whether you want to do it every minute or if you want to do it every 5 minutes, and how many times it has to fail before you want to send the instance as unhealthy. So you can configure your depth, you can configure your accuracy, and you can also get detailed information through API calls also. So programmatically you can check your application and find out what is the health check, what is the status of your EBS health checks. So now we have configured our health checks. Now what ports and protocols I should listen, what is the servers, because you know that you have an application server running on the background and the application server will be listening on certain traffic. But should I configure the same thing on my front end? Sometimes as a security means, people will set up your load balancer for port 80, but your application server will be running on port 8080. So you will receive at 80 and forward it at 8080. So you can have these different types of listeners, and you can listen in one port and forward it to another port also. That is also possible, so that you can add additional security at your application level. So that is all possible by having a concept called listeners, and Amazon allows you to create up to 10 listeners, and each of those listeners can have different rules. Say one listener at port 80 and it will handle order management. Another listener at 80 will handle all your account management. Another listener at port 80 will handle all your static content, or if there is a support queries on all those things. So this way people who are looking for support queries will not be impacted by any sales event happening at a home page, or any people looking at their account profile seeing what are the orders they have made will not be impacted by a sales event, that because all that application traffic is being rerouted to a different group of instances. So that is how routing rules are going to help you. So rules, it is a link between your listeners and the target groups. Say there is an URL and how many application servers or web servers that you set up in the background. The rule is the identity that will link these two, and whenever the condition is met by the load balancer, so there's a tiny amount of processing happening. A URL comes in, the load balancer is going to look at the URL and see whether there is any rule matching this particular URL, and then if it is matching, then it will send it to the appropriate target group. So we need to identify target groups, whether it is an order management target group, or it is an account management, or it is a support center target groups. So rules will be created, and then your target groups will be identified and sent to them. So target groups are nothing but EC2 instances or container instances or your application. It can be anything, but your application team will say I have created 10 servers. All of these 10 servers have to receive only order management related information, related request. These 10 servers are for support related requests. So you will get the IP addresses of those servers or instance IDs of those servers and say this is my target group ABC1, and put those 10 instances under that. So that is how you create a target group, and each target group can have multiple ports. It is not necessary that all the target groups can have same ports. And again, one server can be in part of multiple target groups also. That is also possible. You get all this complex flexibility so that it meets almost all the needs of an enterprise requirement. People say that I have only one server, and that server is acting as a web server as well as an app server, and I'm listening to 10 different ports. Then I want to register the same server to different target groups. Yes, that is also possible. But then there will be a web scale company which will say that I have 10 different servers and each of them are having different ports, and I don't want to mix and match them. I want each of them in a separate target groups. Yes, absolutely possible. You can go ahead and do that as well. So how do you achieve high availability and resiliency when you're using load balancers? That idea here is, once again, use multiple availability zones and create a subnet in all the availability zones that you want your application to be available in, and then put your load balancer in each of them. It is not like you're going to have multiple instances of load balancers, just that an IP address will be consumed from each of those subnets and the traffic will be used using those subnets. So as I keep saying, use high availability, and whenever say high availability, use multiple availability zones and use subnets in each of them and associate them with your load balancers. So that is the architecture that I showed earlier. In this VPC there are two availability zones and each of them having a subnet, and the load balancer is configured, and a route 53 will be there which will be sending traffic to both of them. That is how you achieve a resiliency and multi-IAC architecture in ELB. So in case there is a failure of one of those availability zones or the instance in one of those availability zones, the ELB will get notified of that and it will automatically start sending traffic to that other instance, and after some time, if the instance comes back online, then ELB will recover that. This is another scenario where there is an imbalanced instance capacity. In this case, US West 1A has a bigger instance, like the best configuration that you can get, whereas US West B has 3 different instances of smaller configuration. So naturally the bigger instance being sent with more traffic and the smaller instance being sent with lesser traffic. You can configure it in this way also, so that your cost management is proportional to the type of the instance that you have created. But if you don't want that, then you can do something like cross-zone load balancing. What happens is the ELB will start sending to both of them and the traffic will be distributed to all of them equally. So this is also possible, and this feature is called as cross-zone load balancing, and you can just go ahead and put a check mark in your dashboard and enable this feature. You don't have to do anything crazy for that. Once you put the check mark, it will identify what are the different subnets and whether any instances are there in the other subnet, other AC, and it will start sending traffic to that other instance. So there is no additional charges for this cross-zone load balancing. That is one thing that you need to remember. And it absorbs the impact of DNS caching. Say for example a server goes offline in one AC, the DNS will still might be having that entry of that impaired or unhealthy instance. But if you have cross-zone load balancing and if that instance is not failing, your ELB will understand that and send it to other healthy instance by absorbing the impact of the DNS cache and not sending traffic to the failed instance. So this is a higher advanced level concept. So the traffic goes from DNS to ELB and ELB to the instances. If DNS might still think that some server is healthy because it's still not got an update that the server has gone back offline, but ELB will still know that and not send traffic and send it to the healthy instance only. So if your applications or enterprise customers require cross-zone load balancing, go and set it up. Even then also I would recommend you to set it up because there is no additional cost and it makes sure that the failure is identified earlier and fixed. Finally, as a thematic way of seeing all those things, let us say the load balancer is at the top, then the next thing that you create is a listeners. It can be port level or a protocol level. Once you do that, next you use a target group that you identify, and here there are 3 target groups that have been shown here, and each of those target groups will have some health checks, and the health checks can be at a URL level or at an port level, that is a TCP/IP port checking. Also you can do packets whether receiving or not. So multiple health checks you can configure, and then once you do that, then you launch your instances, and then you can create your rules after your instances are created. Let me see whether the rules are appearing here. Yeah, the rule might be something like a default rule will be sending all the traffic here, and if the URL has something like /image, and then I'll send it to my target group 2, and then there will be a completely different application with a different URL, and that default traffic will be sent to my target group 3. So this is how a load balancer conceptually looks like. At the top level, you create load balancer, then listeners, then target groups, and then you can go ahead and define, or you can ignore your rules. It's up to you how your application traffic wants to be set up. So let us go ahead and set up in our dashboard. Before doing that, I wanted to show you how it works with auto scaling. Here is a simple setup, auto scaling with a couple of servers and load balancing in front of that. And let us assume that CloudWatch is also configured, and constantly your load balancer is going to send information of latency from those two servers, and those two servers are going to send the utilization information. So these two parameters are constantly monitored by CloudWatch, and for some reason CloudWatch notices that something is wrong with one of the servers. Let us say there is a utilization impact on one of the servers, it has gone high. Let us say CPU is more than 80%, or latency is more than 1 second. Then CloudWatch is going to trigger a notification to auto scaling, and in this case let us assume that we are going to do a scale out event. In other words, add one server. So auto scaling will execute that policy. I'm supposed to execute it. I reverted. So it executes the policy, it adds another server to your auto scaling, and it is going to ensure that everything is fine. You can see here, as of now, the load balancer has not started sending traffic. The auto scaling is going to send a notification to a load balancer saying there's a new server. Register this as one of those target groups, and then once it gets a notification, it will start sending to the traffic to that server. So that is how the three services work together. Here we can see EC2, load balancers, CloudWatch, and auto scaling all working together to make sure that your application is having high availability at all times. So this is a simple architecture we are going to do as a demo today. We are going to set up a load balancer in, let us take Virginia as an example, because we will have 3 availability zones, and then we will set up 3 servers and put a load balancer in front of it and try to configure it to hit the 3 servers one by one. Let us go to our dashboard now.